Okay, so let's begin by discussing some of the homework questions from yesterday. And I would like to just open it up, and anybody who wants to ask a particular question about those problems, we should address those first. Any particular questions? Not seeing much here. So, well, so Jordan asked about 2.13. Right? Okay, so yeah, let's go over that together. I don't want to misquote the book. So, this question asks you to find all numbers A and B such that alpha defined by that it takes the point x comma y to ay comma x divided by b is an involution. Okay, so how should we proceed here?
So the first thing I saw is that the default operation, regardless of the constants, is switching the places.
Okay, right, so that is to say the roles of x and y are switched.
Which means that's going to be an involution on its own, assuming everything else is the same.
So, in other words, you're saying if A is 1 and B is 1,
True.
then that choice of A and B results in alpha being an involution.
Yeah.
Okay, good, okay, that's true. So, we see right away if A is equal to 1 is equal to B, then and clearly that's an involution, right? Because alpha of yx is equal to xy. Good. Okay, so is this the only possible choice of A and B? No. No. Okay, so here's my suggestion. Why don't we just operate alpha on the same point twice and see what that gives us in terms of A and B and our original point. Okay. So, in general, alpha of xy is equal to alpha of ay x over b, and then we operate alpha on this again, and what do we get? We get a over bx, a over b y. So, what we want, of course, and we want the point xy to be taken to itself. That would be the characterization of alpha being an involution, right? i.e., this is the result of alpha squared is equal to iota. Okay, so what pairs A and B satisfy this?
Non-zero.
Yeah, they're non-zero and equal, right? Okay, so we must have So I thought, I think the most interesting problem that I asked you to do yesterday is question 2.9. Okay, so let's look at that together. And question 2.9 says, prove or disprove. Every group that contains at least two elements must contain an involution. Okay, what are our thoughts on this? Anybody? I'm seeing some head shakes in the classroom here, but anybody else have any thoughts? So Jordan also thinks disprove. This is seemingly a false statement. Okay, so how can we demonstrate that? Yes. I'm sorry?
Counterexample.
Calculate something.
Yeah.
Is that what you said?
I think counterexample.
Counterexample. Yeah. We'll come up with a counterexample if we want to disprove this, right? And Jordan suggests a cyclic group of order 3.
That's what I said.
Okay. Good.
I need to see pretty specific.
So, in terms of, let me ask you an additional question here related to this. So, abstractly, sure, we can say a cyclic group of order 3. Why don't we try to come up with a transformation group?
I said C3.
C3, okay, so what's the generator? What is the generator?
A rotation by 120 degrees.
Yeah, rotation by 120 degrees, Spencer says. Good, okay, so this is false. Let's let rho be a rotation by 120 degrees. Then the group generated by rho is just iota, rho, and rho squared. Okay? So our claim is that none of these are involutions. What do we have to check to ensure that?
That they're not their own inverse.
Yeah, that they're not their own inverse, or another way of saying that is if we square each of them, except iota. We know iota is not a involution. By definition of involution, we excluded that possibility.
Just from a geometric structure, we can tell that because inverses are unique, that since rho squared is the inverse of rho.
Yeah, I mean, you can write that algebraically just as quickly.
Yeah.
Right? Yep. So let's write that down. We have to show that neither this nor this squared are iota. Well, clearly, rho squared is just rho squared. If I square rho, I just get rho squared, which is not iota. Okay? And rho squared squared, rho to the 4th, which is just rho, which is not iota. Okay? So, has no involutions. Good. Okay, I know sometimes it might be intimidating to come up with a counterexample, but this is the first thing you can try beyond. It's like a very small number, 3, right? Just a group with 3 elements will get you there. I think that's, in general, you are required to come up with a counterexample for something, and you're not sure what to do, start with the smallest examples and see if they satisfy or don't satisfy whatever you're trying to prove or disprove. And just a piece of general strategy there. Okay. Okay, yeah, I also mentioned a couple times that there's this overloading of the term order, right? The order of an element and the order of a group. And exercise 2.6 kind of illuminates why that's not such a bad thing to do. That is to say, those two notions, order of an element and order of a group, coincide when you consider the cyclic group generated by an element. That group must have order, in the sense of a group, that corresponds to the order of that element.
Is it repeat eventually?
Sorry?
It'll repeat and that's off.
Yeah. Okay, so, right, just to reiterate here, 2.6, show that if alpha has order n, then the set of the first n powers of alpha forms a group. Forms a group of order n. Okay, so this is a fairly routine set of verifications, right? So first of all, let's just go through this really quickly. Where does the identity appear in this set? Alpha to the n. That's the definition of alpha having order n. It means n is the smallest positive integer for which alpha raised to that power is equal to iota. Okay? Since alpha to the n equals iota, we have identity property. Okay. How about closure? How do we verify that this set is closed under composition?
I said that you take two numbers, two powers, and have them. Well, the powers is composition. And then if it's less than n, it's going to be in your set, it's gradient, and you can show it as amount something smaller than n, that number minus n, and then continue that process until you get something less than
It's
n.
basically induction, right?
Yeah.
Mm-hmm. Good. Okay, so let's write that out. Take two positive integers, r and s, between n. Okay? Then alpha to the r times alpha to the s. Remember, we have the usual arithmetic of exponents in groups. Okay? And here, of course, alpha to the r and alpha to the s are both in this set, right? Because we chose r and s to be between 1 and n. Okay? And then it breaks into cases from here. So if r plus s is less than or equal to n, we're done. Right? Because that, again, is in this set. Okay? So, alternatively, if then we have alpha to the r plus s is equal to alpha to the n plus r plus s minus n, right? Which is the same by the usual rules of exponents arithmetic. R plus s minus n. And we know that since alpha has order n, we get an iota times alpha to the r plus s minus n, alpha to the r plus s minus n, and then we repeat the argument with r plus s minus n.
The maximum you can have is what? 2n minus 2. But yeah.
Yeah. So you keep doing this, these cases, compare this to n, and then you'll eventually get less than n. Okay? Okay. So,
Inverse was the fun one.
oh, you think the inverse was the
Well, I liked it both. But
Okay.
I just like how inverse was like easy, like still to algebra the same way with that when we go into cases, like the same the cases and stuff like that. They'll count more often.
Okay.
It's the same. Oh, take out the factor of maybe about the end. But you
Okay. So, why don't we say that together? Verify that this set has the inverse property. Right? So, why don't we just take alpha to the r for r between 1 and n, right? Then set s to be equal to n minus r. And compute alpha to the r times alpha to the s, alpha to the r plus s, or in other words, alpha to the r plus n minus r, alpha to the n, which we know is iota, because the order of alpha is n. Okay, yeah, so just again, it all stems from the fact that alpha has order n and just the basic rules of exponents. I'm sorry. Okay, yeah, Ryan has a question here. Why does alpha to the power n equal iota? That is the definition of the statement that alpha has order n. Remember, the order of an element of a group is the smallest positive integer such that when you raise that element to n, you get the identity transformation, iota. Okay? Does that clear things up, Ryan? Okay. Yeah, right. So that's actually what we're proving, right? That the order of an element tells us the order of the cyclic group generated by that element. Okay? And that's why I tried to emphasize this yesterday, that it seems kind of confusing that we use the word order in two different ways, but it's actually intimately related. It's kind of the same thing. That was kind of the point of this exercise. Okay? So, I don't think we need to go through associativity. Yeah, it's fairly trivial. It is trivial.
They are transformations.
Yeah, they're transformations. So, yeah. Okay. Any further questions about anything from the homework yesterday?
Technically, this isn't over. You also wanted to show the infinite case.
Yeah, but I don't think that's necessary to do together. Are there any other questions though? No. Okay. Then, I guess we pick up where we left off yesterday. We were making the Cayley table for the Klein 4 group. Okay, so let me just remind you the two rows that we have filled out already. Okay, so V4, iota, just so my notation is consistent with my notes, sigma sub h, sigma sub v, and sigma sub o. Anybody tell me what V, H, V, and O stand for?
Origin.
Yeah, horizontal. Sigma is a horizontal flip. Sigma V is a vertical flip. I did that in reverse order.
And then planar reflection.
And then O is reflection about the origin. Okay? And we'll see that explicitly in just a little bit. Okay, so this first trivial row, right? And then we had computed together the second row. Okay, and then what do we get here? Okay, and then E, H, and iota. Okay, now, just in case, remember, we have, these are the definitions of these transformations which generate our group V4. Comma Y. Okay, so here's the thing. We had mainly discussed cyclic groups yesterday, and we wrote the multiplication table for C4, the cyclic group with 4 elements. So this is one of the simplest non-trivial examples of a non-cyclic group. That is to say, it necessarily requires more than one generator to make the group. Okay? So, right. So let's compare this group to C4. C4 has only one involution. What is the involution in C4?
Rho.
Right, it's rho squared. Namely, rho squared. However, V4 has how many involutions? 3, yeah. Everything but iota. Yeah, everything but iota is an involution in V4. Has 3 involutions. Everything that isn't iota. Okay? So, right. but I'll write down now. Okay, so C4 is just equal to rho, the group generated by rho, or the group generated by what?
Rho to the third.
Yeah, so you can't, obviously, iota does not generate C4 because the powers of iota are just iota. Furthermore, rho squared, we just said is an involution. So that means we would only get a group of order 2 if we looked at the group generated by rho squared. Right?
Rho squared, yeah.
Right. So if you look at rho cubed, the only remaining element of C4, look at successive powers of that, and you get all the elements of C4. Whereas V4 can be generated by sigma H and sigma V, or sigma H and sigma O, or sigma V, sigma O. Any pair of the involutions generates V4. Okay? So, here's perhaps the slightly surprising thing, right? First, let me just draw you a couple pictures, and then I'm going to show you that C4 and V4 actually have an element in common. You see? Okay, so here's a graphical depiction of what sigma H does. I have my Cartesian plane, and let's just say I have an indicator arrow here to see what this does, right? So, this gives me, okay, so I operate sigma H on this, and I get this arrow here. I made my, oh, sorry, no, Y. Y is negative for H. I get this arrow here, right? Okay, so sigma V, similarly, I take this same arrow, and then in the plane, and I operate sigma V on this. I get this arrow here. Okay? Sigma O. Again, I have my plane and this test arrow. And I operate sigma O on the plane. And what do I get? I get this. Okay? So, pictorially, I can see that sigma O is equal to rho squared, right? If I take this arrow, apply rho, I get this arrow, apply rho again, I get this arrow, okay? So again, There's some non-trivial relationship between rotations and reflections. Okay? And, oh, I'm sorry. Okay, so Keenan asks, did I switch H and V here? So H in the textbook.
H is the H is over the x-axis. So yeah, that's right.
Yeah, it's negative y, right? So yeah, I think this is correct. Unless you asked that question when I first wrote the wrong thing and I missed it. So yeah, this is right. Okay. Right, so this is our first clue that there's some perhaps more interesting non-trivial structure that we can discuss between reflections and rotations. Okay, good. And we'll talk about this in great detail soon. Okay, so I just want to say a couple things about groups in general. And we're not going to do a long systematic study of groups in general, but I just wanted to give you some view of what the next step is if we were to continue studying group theory, which many of you will, or perhaps already have. Some basics of group theory. Okay, so first of all, technically, the definition I gave you for a transformation group is based, in particular, on transformations. I'll tell you the general definition right now. So, group is a set G. Well, actually, I guess we've been using cursive G. We'll stick with that. Set G with a distinguished element one sub G and a binary operation. We'll just call it dot such that the following hold. A and B elements of G implies that A dot B is an element of G. Closure. One sub G dot A is equal to A is equal to A dot 1 sub G for all A in G. Three, for A in G, there exists B in G, so that A dot B is equal to 1 sub G is is equal to B dot A. And finally, for A, B, C, all in G, then A dot B dot C is equal to A dot B dot C. Okay, obviously it's extremely transparent that these are exactly the same axioms, the same properties that we insist a set of transformations have to be a group. Why did I bother saying this? Well, the important distinction is we don't know, we haven't specified anything about this element 1 sub G. When we talk about transformations, we know explicitly what that thing is. It's the identity transformation. But for an arbitrary group, it could be much different, depending on what kind of set G is. Okay? Same deal with the definition of dot, whatever the binary operation is inside the set G. Right? Composition is the natural thing to choose when we talk about transformations because they have the structure of functions in the first place with the same domain and codomain, so we can compose them freely. Okay? Again, it depends on the type of set that you're dealing with, what you can define as an operation. Okay, and the reason that I wanted to take this step in generality is because despite one of the beautiful things about group theory, the reasons why it was developed is because despite having different types of sets and different operations and different identities, you can still identify the same group structure, the same multiplication table. Okay, so that's kind of the main thrust of why people started to do group theory in the first place. Is because you can somehow translate structure into a more inviting environment, depending on the type of problem you want to solve. Okay? Hopefully I won't philosophize too much today, but I had to get some in there. Okay. So, let's see. Okay, so now, how do we do this? How do we identify when a group has the same structure as some other group? Well, you could write out the multiplication table and compare them. That's a bit cumbersome in general, and in fact, we did discuss it's possible for G to be infinite. So then writing down the multiplication table becomes quite a bit harder or impossible. Okay? So here's another way. Okay, so let's suppose G and G prime are two groups. Okay? And there is a function f going from G to G prime so that for all A and B in G, we have f of A dot B is equal to f of A dot f of B. Then we call F a homomorphism. because there are different types of algebraic structures that also have this concept of a homomorphism. But of course,
Preserving the operation.
preserving the operation. Now, there's a subtlety here. This multiplication, A dot B, happens in G, right? Our domain group. This dot happens in G prime.
Regardless of the operation is the same.
So what we say is that F preserves the operation. It takes the operation that happens in G, it takes the group operation, and translates it into the group operation of G prime. Okay? So if you take the view that you can determine the structure of a group by writing down its multiplication table, this is kind of, okay, we want to consider functions from groups to groups that preserve multiplication. Okay? The operation is kind of the key feature that determines what a group is or does. You know? That's a little vague, but it's a good intuitive place to start for what groups are all about. Okay? So, furthermore, if F is bijective, then we call it geez, an isomorphism. Okay, so this is what we want. When I say, oh, I want to determine if two groups are quote unquote the same, what I mean is I want to construct an isomorphism. I want to construct a bijective function that preserves the group operations. So that's the technical workaround from actually having to write down the multiplication table. If you can construct a bijective function that preserves multiplication, then you've shown that these groups have the same structure. Okay? So let's look at a couple examples. One, not so hard. The other one, kind of surprising. All right, so let's let G just be a set consisting of two matrices. The identity matrix and the negative of the identity matrix. With binary operation, matrix multiplication. Okay, so not surprisingly, the identity matrix is the identity of matrix multiplication, right? Take any matrix, multiply it by the identity matrix, you get that matrix back. Okay, and then furthermore, let's let G prime just be the set of integers 0 and 1 with binary operation, addition modulo 2. It's okay if you're not familiar with this terminology, addition modulo 2. What does that mean? What that means is, okay, quick overview. What this means is, to add integers modulo 2, I guess I should say add integers a and b modulo 2. All you do is consider a plus b, the usual addition, okay? And if even, a plus b equals 0. If odd, a plus b is equal to 1. Okay, it's just distinguishing between even and odd. Is that okay? Yeah, Thomas, I assume that was the question, right? Like, what does modulo mean? It means you're just paying attention to whether your sum is even or odd. Okay? So, in other words, mod 2, e.g., modulo 2, 1 plus 1 is equal to what? 0, right, it's even. And, really, I should put these equal signs in quotation marks. Yeah, but we're not going to introduce that notation. The type is a looser thing than equality. Congruence, but
yeah,
that's neither here nor there. Okay, so we have these two groups, right? We have these two groups, and I claim the function f from g to g prime defined by f of, the identity matrix is equal to 0, and f of the negative of the identity matrix is equal to 1, is an isomorphism. Okay, so what we have to check here is that every pair of things that we can multiply together in G gets mapped to the sum mod 2 of what we say they are in F. Okay, so to show this, for example, compute f of, okay, let's take the identity matrix times the negative of the identity matrix. Well, on one hand, we just get the negative of the identity matrix here, right? And just by definition, this is equal to 1. Okay, so that's one way of computing f of this product. Now, we should compute f of each of these, take their sum, mod 2, and see if we get the same answer. Okay? Oh, I should mention, what we're doing right now is to show this is a homomorphism. It's an isomorphism because it's obviously bijective. Right? I have two elements in G and two elements in G prime. And each element in G goes uniquely to an element in G prime. Okay? So, showing that it's bijective is trivial because they're two sets of size 2.
It's really easy to check.
Yeah. Okay. On the other hand, let's compute f of the identity matrix plus f of the negative of the identity matrix. Okay, so here it becomes more transparent about when you're operating in G, when you're using the operation of G, and when you're using the operation of G prime. Inside F, we're using the operation of G. When we add the result of F, or when we combine the result of F, we have to use addition, mod 2, the operation of G prime. Okay, so again, by definition, this is 0, and this is 1. So we check that this works for this product in G. Okay, now if I want to do it in general, I would just take arbitrary matrices, A, B, C, D, but they're so small, it's really 3 things to do. Okay, let's do one more. I don't want to spend too much time on this, but let's do one more together. Okay, so
Just made a hard one.
no, it won't be hard, but we will have to use modular arithmetic. What happens when we square the negative of the identity matrix? F of negative identity times negative identity. Well, in G, what is negative identity times negative identity? The identity, yeah, good. Okay, so we want to compute f of the identity. Well, by definition, this is just 0. Okay, now let's compute on the other hand what happens if we take the sum in G prime, mod 2, of f of the negative identity and f of the negative identity. Okay, so again, by definition, this is 1, this is 1, this is 1 also, which is equal to 2. Mod 2, this is even. Okay, so if you really want to, you can verify the last multiplication, the identity times the identity. And then you will have proved that f is an isomorphism. I don't think we need to do that together though. Okay, so let's do one more example. We won't actually verify that this is an isomorphism, but it just shows that why this concept of isomorphism is interesting. That we can actually come up with some surprising relationships between groups that don't seem that related. Okay? So let's let G just be the set of all real numbers with binary operation. Addition, usual addition of real numbers. And let's let G prime be a set of all positive real numbers. That's common terminology, but I haven't introduced it. With binary operation. Multiplication. So, my claim is that G and G prime are isomorphic. Okay, so, I mean, of course, the real numbers are quite large, uncountable, but still, you might think by cutting them in half, somehow, considering only the positive ones, that...
Identity has mapped to identity, right?
Yes, so that is a consequence.
0 has to equal 1.
Via some homomorphism. Yeah. Okay, so I claim it's a terrible G. G and G prime are isomorphic. Okay, so any guesses as to what function we can show is an isomorphism?
Oh, wait.
Yes?
E to the variable.
Yeah, good. So the suggestion was the exponential function. Yeah, good. So define f mapping G to G prime by f of x is equal to e to the x. E to the x. Okay. This is an isomorphism. And this isn't a proof, but let me just show you something, right? Obviously, if we take f of x plus y for some real numbers, x and y, we get e to the x plus y, or in other words, e to the x times e to the y. Okay? So, we've translated addition into multiplication. Alright? So there's a lot of things to verify here about this actually being an isomorphism. Most of them are just facts about E, right? We're not going to talk about that. I just wanted to, because this is not a course in group theory at large, I just wanted to illustrate why this concept of isomorphism is valuable to us. Because these, I mean, although, okay, so the underlying sets of these groups are sets of real numbers, so there's some relation, but on the face of it, like, oh, not knowing anything about functions, like what's the relationship between R with addition and positive reals with multiplication? Hard to say, really. So that's kind of the value of this concept of isomorphism. Yeah, so in fact, I want to just write that down. Groups that are isomorphic can be thought of as the same. That is, they have the same Cayley table and the same set of subgroups. They behave exactly in the same way. Okay?
Every other group texture is the same down to the elements. Like the elements are making different. The making the same one.
It's really just a relabeling.
Yeah.
A particular isomorphism is just a relabeling of the elements of a group. Okay? So, I wanted to come back to a point that Zach mentioned, I think that's worth noting, about homomorphisms in general. Notice that for any homomorphism, F mapping G to G prime, we must have that F evaluates the identity of G to the identity of G prime. Okay, why is this? Since for any alpha in G, what can we say?
That the operation of them together inside is the same. It creates just the output of alpha on its own.
Okay, so if we take f of alpha,
That's the same as f of 1 sub g times alpha.
this is the same as 1 sub g times alpha. And since f is a homomorphism, we can split this in G prime. Okay, and again, I'll just write this for emphasis. This is in G, and this is in G prime. Right? Yeah, so we have f of alpha is equal to f of the identity of G times f of alpha. So f of the identity of G equals the identity of G prime. Okay? Okay. So it may be the case later on in the course that we will perhaps require just a little more group theory, but we'll just go over whatever's necessary as we go. That's all I'm going to say about the basics of group theory right now. Okay? Any questions before we move on? So now, what we're going to do is, remember, when we started talking about transformations, I gave you some intuitive examples, translations and rotations. Now, we're going to go back and do that a little bit more rigorously. We're going to justify why translations first, and then eventually rotations, form not just transformations, but actually subgroups of collineages. Okay? These will be our first examples that we care about of transformation groups.
So you can see they preserve lines geometrically, so it makes sense.
Yeah, so we should do that in a formal fashion. Okay, so let's first discuss translations. Okay, so here's the definition of a translation. A translation is a transformation determined by two numbers, A and B, as follows. Alpha of xy is just equal to x plus a, comma, y plus b. Okay, I think when we discussed on Monday, I believe, the intuitive example, I think we had a equal 1 and b equal 0. And we just had the shift over 1, 1, 1, 1. So anything of this form is a translation. Okay? So, here's the cornerstone of how to characterize translations in a synthetic way.
Wait, synthetic geometry?
Yeah.
Okay.
Yeah. It will prove it analytically, but the statement is synthetic. Okay, so given points P and Q in the plane, there is a unique translation sending P to Q, which we denote tau sub P, comma Q. Okay, so let's take specific coordinates. then we can set tau sub p comma q of x comma y equal to x minus, I'm sorry, plus x2 minus x1, comma, y plus y2 minus y1. Okay? So, this certainly takes p to q. So, we must show that it's unique. Right? Everybody see why this takes p to q? Right? If I put p in here, I put x1 here, x1 cancels with x1, y1 cancels with y1, and I get x2, y2, which is just q. Okay? Is that all right? Okay, so let's say, suppose tau is some other translation such that tau of p is equal to q. Okay, and then our goal is to show that tau is equal to tau sub p comma q. Okay, so so this implies that since tau is a translation, we have some formula. There are two numbers, a and b, such that tau has the formula x plus a comma y plus b. Right? Then tau of p is x1 plus a, y1 plus b. Right? And
Q.
this has to be equal to q, which is just x2, y2. Okay? So whenever we have an equality of points, this is actually two equations, right? So that is to say this is x1 plus a is equal to x2, and y1 plus b is equal to y2. Now if I solve for a and b to determine what tau was, what do I get? I just get the original a and b that I set for tau sub p comma q. So altogether, this implies that tau, any other translation that sends p to q, is equal to tau sub p comma q. Okay. So this theorem has a bunch of interesting consequences about how translations behave. So, for example, due to this theorem, we see, for example, that if tau sub p comma q of r equals s for some points R and S, then what do we know? Well, tau sub p comma q is a translation, right? It's a translation that takes R to S. And there's only a unique translation that takes R to S.
Using Euclid's axiom.
Well, that'll come in when we talk about collineation, how these are collineated. But for now, what this means is that tau sub p comma q is equal to tau sub R comma S. Okay? Because tau sub p comma q is a translation that takes R to S. And what we just proved is that there is a unique translation that takes a given point to another point. Okay? Okay. So in other words, there's lots and lots of ways to specify a given translation in terms of points. Okay? Take an arbitrary translation and find the image of a given point. You can write that as tau sub RS. Tau sub your input, comma your output. Okay? So, also note, iota is a translation. Take these bullet points. Right? What are the A and B that specify iota as a translation? 0, 0. Yeah, we let both A and B be equal to 0. Okay? And using my first bullet point here, what's an alternative way to write iota in terms of this tau notation?
Tau sub p comma p.
Yeah, exactly. We can write tau sub p comma p, so that is equal to iota for any point p, right? Because iota is the thing that takes every point to itself. Okay? So, let's see. Another way to say this, this allows us to conclude that if tau sub p comma q of R equals R for some point R, well, that implies that tau sub p comma q is equal to tau sub R comma R, in other words, iota, which in turn implies that the points P and Q that define tau originally are equal.
It keeps any point the same, it keeps every point the same.
That's right. If a translation has a fixed point, it's the identity. Okay? Okay. So, let's see. Yeah, I think we have just time to do this today. Good, we're a little bit ahead of schedule. If you're following along in the syllabus, you'll notice that we weren't supposed to start translations until Monday. But this is good. Maybe we'll have time to do some space stuff at the end of the summer. At the end of summer 1. So, let me give you a preview of what we're embarking on right now. We're going to give the first transformation geometry criterion for answering a classical geometric problem. That's what we're aimed towards now. And I'll tell you what that is right now, and then write it again formally after we reason some things out. But the problem is to determine if a arbitrary quadrilateral is a parallelogram. Okay? So, you know, from a practical, real-world standpoint, it's like, oh, let me just take some measurements and like see how long the sides are and what the angles are in the interior of this quadrilateral. But how do we deduce that geometrically?
Knowing the lines. What do we know?
We know that we have 3 non-collinear points, and we take an arbitrary fourth one.
Okay.
Okay, so yeah, and that's what we'll puzzle out before I make the formal statement. I just wanted to give you an idea of where we're headed. Okay, so let's let T be equal to a point A comma B, and we'll also take P to be equal to a point U comma V. Then the translation taking the origin, which remember we denote O, to T is given by tau sub O comma T, X comma Y, is X plus A, comma Y plus B. Right? I started, if you look back at our formula for tau sub P comma Q, I used the coordinates of P and Q to determine these A and B. My coordinates for T are A and B. My coordinates for the origin are 0, 0, right? That's why they don't appear here. Okay? So, let's set Q equal to this transformation, tau sub O comma T, evaluated on P. Or in explicit form, this gives us U plus A, comma V plus B. Okay, so by what we deduced over here, we know that, so tau of sub O comma T is equal to tau sub P comma Q, right? Because tau sub O comma T takes P to Q, so we can write it as this. So at this point, I'm just going to draw a little schematic diagram for you all. Let's say our origin is here, and we have our point T. This is what our translation, tau sub OT does. It moves the point O to T. Okay? But we're also saying that for some other point, P, which the image under our translation is this point Q. This is again the same translation, but this time expressed in terms of P and Q.
So your fourth point's not that one.
I'm sorry?
Your fourth point's not that one.
Well, so we're actually doing more than the result that I told you we'll get to. We're working in greater generality, and we'll just specialize to that case. Okay? Okay. So now let's be very analytic about this. I mean, I've drawn this picture very suggestively, but we don't know that these are parallel. We can know it, but we haven't justified it yet, is what I mean by that. Okay, so let's use the distance formula. So what's the distance from the origin to t? So this is notation that the book uses. You just put points next to each other, and that means the distance between the points. I don't like that notation particularly much, but the book does use it, so I guess we're stuck. So what's the distance from the origin to t? Well, we just do that in coordinates, right? We have a minus 0 squared plus b minus 0 squared, or in other words, square root of a squared plus b squared. And how about the distance PQ? Well, here I have u plus a minus u. Am I using the right notation? Yeah. Squared plus v plus b minus v squared, which of course just reduces to the square root of a squared plus b squared. Okay, so they're the same length. Furthermore, I can calculate the slope of the lines through the origin in T and P and Q, respectively. And again, notation that I'm not particularly fond of. The book specifies these lines as this, a line over OT. It means just the line that's through those, the unique line through those 2 points. So OT has slope. Well, we just use the high school formula for slope. It's the change in y over the change in x, right? So we take the y component of t minus the y component of the origin divided by the x component of t minus the x component of the origin. Has slope b over a. And the line through PQ has slope minus v over u plus a minus u, or b divided by a. So what does this mean? This means that the line through OT is parallel to the line through PQ.
Parallel, has the same length.
Yeah, is parallel. Is what this double bar means. Okay? So, as long as t is not equal to O. Okay? Because then we would just have tau be the iota, the identity transformation, if t were equal to O.
Is that a parallelogram?
Degenerately, maybe.
Yeah, okay.
Right. So, classic theorem. A quadrilateral is a parallelogram if and only if two opposite sides are parallel with same length. Okay, so this is one of those things from Euclid's Elements. This is like a very old, synthetically derived result of geometry. Okay, so what have we shown? Well, one consequence of what we've shown is what I was saying at the outset of that derivation. Maybe I shouldn't have erased that. Here's our theorem. Suppose A, B, and C are non-collinear in the plane, right? Non-collinear, of course, meaning that they all three don't lie on the same line. Okay? Then what we have is tau sub A comma B is equal to tau sub C comma D for some other point D, if and only if the quadrilateral formed by C, A, B, and D, which sometimes is written box C, A, B, D. Okay, again, this is kind of old geometric notation. Is a parallelogram. Okay, so this is, on the face of it, it seems like we didn't actually do that much. But what we've done, the result, is that we can take an arbitrary quadrilateral, and now we have a mode, an easy method to check if it's a parallelogram. Because transformations have such a nice, simple form.
So just subtract the point values even.
Say again?
Just subtract the point values even.
Yeah, yeah. Right. So, even though we didn't actually do that much, the result is very powerful because it provides us a way to address this old problem of determining when a quadrilateral is a parallelogram to something very computational. Okay? And that's kind of, this is our first glimpse of how transformation geometry helps us reconstruct Euclidean geometry and perhaps go even further.
It also is helpful for like constructing when it's not aligned.
When it's not, I'm sorry.
When it's not like an easy like take these coordinates.
Yeah, it's also useful in less constructive situations. Yeah. Yeah. So, right. I think we'll stop there for today because then we're going to talk about how translations are collineations, and then talk about a certain subclass of translations. And these will be our first two important examples of transformation groups. Okay, so before we go, I just wanted to reiterate, sorry again for missing office hours yesterday. I don't know if everybody saw my message, but I was locked out of my house for a while. I have my keys with me today, so there'll be office hours this afternoon as well, 4:30 to 6, to make up for the office hours that didn't happen yesterday. And sometime this evening, I'll make an announcement on Canvas about review material for the first exam. Okay? Yeah, great. So have a good weekend, and I'll see you all on Monday.
I have